Study of heat and heat transfer. In fact, if you are in engineering, if you major in engineering, you'll probably do an entire semester course just on thermodynamics. The idea is to kind of look at engines, how engines work, and heat engines and things like that. It's kind of like chapter 24. It really relates to chapter 24, but we need the material in 21, 22, and 23 to kind of understand what's going on in 24. Also, as an oceanographer, heat transfer is very important in understanding how heat flows through systems, how this energy goes from place to place is very important. You know, how does it go through the atmosphere and the ocean and the crust and things like that. Now, you'll see me abbreviate it T-dynes because I get tired of writing thermodynamics over and over and over again, as you probably will too as we go along. So if you see me write T-dynes, what I'm talking about is thermodynamics. But the first thing we're going to talk about is temperature. Temperature. Our symbol for temperature is a capital T. Now, the units we're going to see are degrees C and Kelvin. So, degrees Celsius and Kelvin. These are the two scales that we use in here. Although we are going to talk about Fahrenheit. Now, there are lots and lots of temperature scales. Okay, so on that, I mean, we can make up our own temperature scale on this. You know, we could use the Megan scale. Everybody has to use her thermometer. She makes a thermometer, everybody uses it. Now, we would have to figure out how does it relate to other thermometers on that. This is the problem some of the early people with thermometers doing temperature readings and things like that. There's been thermometers. I mean, Galileo made thermometers and things like that. But there's lots of temperature scales. But there's one thing about all temperature scales. Not only do they measure how hot or cold is, which is kind of the elementary school definition, the one we want, they all measure average kinetic energy. The average kinetic energy of the atoms and molecules. And because it is an average, how many molecules are we actually talking about? When we talk about an average, we're always taking lots of numbers and making it into one. Remember, we're talking about it's the average one molecule. Always keep them in mind. Average one molecule or atom. But so this is talking about the average kinetic energy. We're talking about speed here because as we add energy to something, its kinetic energy is going to go up. As we take energy away from something, its kinetic energy is going to go down. But the mass is not going to change. I mean, if I have a little beaker, if I had a beaker of water, the mass of the water molecule is changing? No. But the speed is. Now, notice it talks about an average. If I had this with water in it, there would be some fast ones, really, really fast ones that are on the verge of boiling. And there would be some very slow ones that were almost at absolute zero. But there's also going to be a whole lot in the middle. And we're talking about the average. What is the average in that sample of all those molecules? Like that. But one thing we also have to understand, we're going to talk more about it next time, but they're going to mention it in the movie. Let's think about as these things move more, and then everything moves. Anybody need more time on this? That all particles move. Even in your table, they're vibrating. The little molecules are vibrating. In the water molecules, they're moving around. Gas molecules, they're moving around. The more they move, the farther they're going to get apart. The less they're going to move, the closer they're going to get together. It's kind of like this. If I took you all to the gym and I made you stand in the free throw circle, or we went to center court, there's a circle of center court, made you all stand in that circle. If you stand still, that's pretty easy. If you guys start moving around slowly, could you still stay in that circle? Would you still be as close to each other, though? No. I said, okay, now you all have to run as fast as you can. Would you be able to stay in that circle? No, you spread out. Same thing happens with our materials. A very simplistic view of it, but as things heat up, they're going to spread out and things like that. As they slow down, they can get closer together. And energy-wise, so if we're talking about water, gaseous water, what do we call gaseous water? It starts with an S. Steam. Gaseous water will have more energy than liquid water. Liquid water is going to have more energy than solid water on that. So in a substance, so gases will have more, solids will have the least, and that saves substance on that. Now, one thing I want to make it clear: can we see steam? Can you see steam? Steam is invisible. Steam is invisible. If you see it, like you see something running, you see this big plume of white stuff coming out, that is liquid water. All that white stuff is liquid water. Just like up in the clouds, that is liquid water. Those are little teeny tiny droplets of water. But it's liquid. If you can see it, it's liquid. You cannot see steam. Steam is invisible on that. That's why when we look for steam leaks on a steam-powered ship, when you look for a steam leak, you look for it with a broom. You run a broom along the steam pipes, and when the broom disappears, because it vaporizes when it hits the steam, you know you found the leak. You don't use your hand because the same thing would happen to your hand. Go right along, no hand. Use a broom. All right, so we're going to watch this little video. So there's about measuring temperature.
Eureka! The story so far. When matter, in any of its three states, gets hot, its molecules go faster and take up more space, and the solid, liquid, or gas expands. When matter gets cold, its molecules go slower and take up less space, and the solid, liquid, or gas contracts. And now, measuring temperature. Can you tell whether something is hot or cold? In that case, decide which of these three bathtubs you'd like to step into. This one, which is freezing cold, or this one, which is boiling hot, or this one, which is neither too hot nor too cold. It's an easy choice, isn't it? Well, go on. Step into the middle one. Feels just a bit too hot, doesn't it? Try the other foot. Oh, now it feels a bit too cold. Well, perhaps judging whether something is hot or cold isn't so easy after all. This is because the human body can only notice differences in hotness or coldness, how hot or cold something is in comparison with something else. But even your own feet can't agree about how hot or cold the water in the middle bathtub is. There must be a better way to measure degree of hotness, or temperature as we usually say. What do we know about hotness? Well, when the temperature of something goes up, its molecules go faster. The molecules in the boiling hot bath water are going too fast for comfort. And the molecules in the freezing cold bath water are going too slowly for comfort. If we could only make sure that the molecules in the in-between bath water were going at just the right speed for the human body, you could take your bath. But how can we measure their speed? Molecules are so tiny, we can't even see them, let alone clock how fast they're going. Wait a minute. There's something else we know about hotness. It not only causes a speed up of molecules, but this speed up causes matter to expand. So we could measure molecule speed indirectly by measuring the effect of that speed, the expansion itself. And that's exactly what a Swedish scientist by the name of Anders Celsius did in 1742. He took a liquid that expands quite a bit when it gets hot, mercury, and poured it into a little tube. He then put the tube into some freezing cold water, and the mercury contracted down to here. He decided to label this freezing point of water 0 degrees Celsius. Next, he put the tube into some boiling hot water, and the mercury expanded up to here. He marked this boiling point of water 100 degrees Celsius. Now he had a means of measuring the relative speeds of molecules. In other words, the relative temperature or degree of hotness of things. comfortable room temperature is 20 degrees. But 30 degrees is a bit too hot. And minus 20 degrees is much too cold. Celsius could even take his own temperature and find it to be about 37 degrees, which, naturally enough, is the ideal temperature for your bath water, normal body temperature. All you have to do is adjust the water to 37 degrees, and you'll finally be able to take your bath, courtesy Anders Celsius and his hotness meter. Or if you prefer the Greek word for hotness, which is thermos, as in thermos bottle, his thermos meter, or thermometer. Is your bath water at the right temperature now? Oh, my. Perhaps you should have taken a shower.
Well, there's lots of types of thermometers, although the video kind of makes it sound like that Celsius invented the thermometer. He didn't. Thermometer has been around a lot longer. Not always looking like the thermometer that we use. Now, a lot of times because of what we use digital thermometers, little things that look like that. But I'm sure at home you may have thermometers like, thermometers that goes in the ear. They'll go to the doctor, they look at your ear, that's a thermometer. Other science classes, you might use thermometers that had red, yellow, red, green, blue liquid inside. These are spirit thermometers. In other words, they have alcohol inside. If you have a thermometer that's silver, that's mercury. Now, mercury thermometers are more accurate than alcohol thermometers, spirit thermometers. But when you drop a spirit thermometer, you sweep it up, clean it up with a sponge, and you're done. You drop a mercury thermometer, and you call out the hazmat team and rip up the floor and all kinds of nasty things like that. Not very simple. But even some of the early thermometers, I'm sure these are now decorative things. It's called a Galileo thermometer. Galileo used thermometers like that, some of those early people. And this works on the density of liquids. You have this kind of this oily stuff in here. And as it expands, it becomes less dense. And you have these little balls, and they have certain densities and certain temperatures. When we get to a certain density, it'll sink. So the ball, basically if there's several balls at the top, whatever was at the bottom, that's the temperature. So they have a little disc as a temperature. But is that very accurate? No. But that's what many of the early thermometers were. And it progressed along. But there's one thing about all thermometers. They all measure a certain amount of change of kinetic energy. When you see that thermometer move a little mark, it represents a certain change of kinetic energy in that substance. Has the kinetic energy gone up, or has the kinetic energy gone down? That's the thing to always remember. But different scales, obviously, that's going to be a different amount. But how could you make a simple thermometer?
The difference between hot and cold are one of the first